Instructor Carlos Plain of Durham School states, "Totally, I went through my entire time on Earth empowering an unequivocal hypothesis of the universe. Additionally, at last, the hypothesis is being tested. I welcome that, since that is the way we push ahead. That is how we gain ground in science." The James Webb Space Telescope is upsetting and remarkable measure of what has been seen as truth in cosmology. For the new year, another ultra-deep image shows that we have serious goofs in cosmology. The telescope, which should show us the fundamental stars of the universe, is evolving into a foe of the past perspective, and may present to us a thoroughly astounding science. Not all experts are quailing in dread at the new realities. Other well-informed specialists welcome the progressions, since it has for a genuinely long time been clear that something was the matter with our old speculation. The deviation in the assessment of the progression speed of the universe alone should have shaken specialists' perception in the past. Yet, bringing everything into account, they stuck to old theories. The cosmic microwave background, CMB radiation, considered the most settled light in the universe, was made something like 380,000 years after the Big Explosion, exactly when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Researchers call this interaction reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were dealing with another type of radio-receiving antenna technology. This revelation was, for a long time, seen as possibly the most robust piece of proof for the theory of the old Big Bang, earning Penzias and Wilson a Nobel Prize and an irrefutable spot in the history of astronomy. The CMB most likely offers a viewpoint on the early universe with little temperature contrasts, giving fundamental data about the conditions not long after the Big Bang. Specialists included the CMB as a solid scratching of the fundamental assessments of the material universe to check the progression speed of the universe, among other things. The cosmologist Edwin Hubble had already settled this in the late 1920s, finding that faraway galaxies retreat from us and that their speed is corresponding to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level surveying techniques available many years later, at the point when the CMB was found, which led to a recalculated development rate. These were all around lower than Hubble's original figure. Later, experts recalculated the rate utilizing type Ia supernovae as standard candles, giving stable light that could be used as a dependable measuring point. The estimates within the CMB yielded a development speed of around 67 kilometers per second per megaparsec, while estimates using astronomical blasts yielded around 74 kilometers per second per megaparsec. What does this divergence in determining the advancement speed of the universe truly tell us? Did you know that this goof has been known since the 1990s? Since that point, analysts have known, or at least thought, that something may be the matter with the examination of the CMB, the evaluation strategies, or the possibility of the universe's extension. The abnormality between the observed and predicted values of the development rate is referred to in science as the SAA strain or Hubble strain. The ramifications of this strain are tremendous, showing that fundamental bits of how we grasp the universe may be imperfect. For a long time, specialists were puzzled. Since the James Webb Space Telescope went into action, it has furnished experts with stunning information that may now reveal data on the issue of the advancement speed of the universe, with systems so old and mature that their advancement should have begun hypothetically before the Big Bang, disrupting old cosmology. Analysts no longer discuss mistakes or evaluation contrasts. They discuss the emergency in current stargazing. Not only could the improvement rate be off, but the entire idea of development or the Big Bang itself is being called into question. Pictures from the telescope give proof of a universe completely startling from what we have long thought. The SAA pressure was the chief scold to specialists who still have confidence in old speculation. Now they face an issue. Do we, in fact, understand the universe? Different researchers stand on the remnants of their once brilliant source of both discovery and torment, exploring space with fear and wrestling with what they find. Taking into account the emergency in science, we should ask ourselves, what do we, in fact, know about the universe? To answer this, we truly need to grasp how science functions. Speculative experts utilize a multifaceted plan of mathematical models, careful data, and smart reasoning to move ends from the general to the specific. Their understanding comes from a blend of insight, credits, significant outcomes, and speculative appraisals. The term hypothesis alone shows that these are advancements and contemplations, not outright bits of information. The primary critical data we have are the photographs telescopes provide, the sound waves and radiation accumulated with radio telescopes, and the most recent data from neutrino studying systems or gravitational wave indicators. With the James Webb Space Telescope, we now have an instrument that can part the light into individual frequencies and break it down in amazing ways. Webb can show us the essential part of galaxies in the early universe, billions of years ago, how much mass they contained and the number of stars present. Can also follow the shape and course of a galaxy's development. Webb, however, has limits. For example, it can't continually totally decide whether we are seeing galaxies or, on the other hand, black holes with immense gravitational forces that emit as brilliantly as a galaxy. We should face the reality that our science has long accepted an extreme number of potential results as facts while excusing elective clarifications. Research has for quite a while been certain about its accuracy. The most recent disclosures from the James Webb Space Telescope are fundamental signs to replace theories with new insights, as has occurred in general in science. Analysts are eagerly anticipating the new disclosures, which are unexpectedly astounding, and different specialists are striving to develop new clarifications. The new revelations shake the underpinnings of our ongoing science, disturbing many specialists. The current models of real science are still largely founded on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the reality of this world and the universe for a long time. Newton's principles describe the movement of objects under normal conditions and function particularly on Earth. However, in space, his hypotheses required development, generally completed by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpreted reality, showing that events are relative to each other and depend on the observer's movement. His general theory of relativity, published in 1915, extended this thought with mathematical representations of gravitational traits based on the curvature of spacetime by masses like stars or galaxies. Einstein's principles and ideas were significant in many areas. However, he too recognized their limitations. He knew his theory would never fully describe the universe and yearned to see a unified theory, which he never achieved. No other expert has reached this stage either. Wouldn't it be fascinating to know where it lies? Mido Kaku, an unmistakable astrophysicist from the USA, said in an interview that addressing this issue would certainly win a Nobel Prize. Could we explore whether the experts might have missed potential misinterpretations or whether our telescopes are to blame? Dark matter and dark energy are at the top of the suspect list for the crucial reasons for the cosmological emergency. Our developing models of the universe incorporate ideas that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They probably don't exist in any form or shape, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. On the other hand, they could have properties we don't yet appreciate. One thought is that the true properties of dark matter and dark energy have changed over time, potentially showing some type of evolution. Gravity is another hypothesis to be tested. This force, which creates attraction through mass or curvature in spacetime, has not yet been fully explained. The concepts of spacetime, which originate from Einstein and have been customarily upheld, may require revisiting. We can't rule out the possibility that gravity has unexpected properties or that another force is responsible for the gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our constant search for understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes exploring the depths of the universe. Each step toward improvement and theory has revealed new mysteries while challenging established beliefs. In the realm of cosmology, the James Webb Space Telescope, JWST, remains a beacon of our scientific advancement, promising to change how we interpret the universe's origins and evolution. Launched with remarkable capabilities, JWST represents a leap forward in observational space science, designed to look further into the universe than ever before with unprecedented accuracy in examining radiation. The CMB, often referred to as the glow of the Big Bang, offers a perspective on the universe as it existed shortly after its first interaction with the world. This ancient form of radiation carries fundamental data about the universe's early conditions, including its temperature variations, which are crucial to understanding the development of galaxies and large-scale structures. The disparity in the calculated values of the Hubble constant, known as the Hubble strain, has been a subject of prolonged debate. It suggests that something is wrong with our basic understanding of the universe and its early structures. Discoveries challenge conventional theories and require a reassessment of whether our perspective on cosmic expansion is fundamentally flawed. New insights might uncover hidden parts of the universe's creation, raising questions about dark matter and dark energy, two unexplained components that make up most of reality. The progression of science depends on the ability to reshape our theories in light of new information. Webb's mission exemplifies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and should shed light on new perspectives on the universe's mysteries. The future of cosmology might witness tremendous changes, leading to significant implications for how we interpret the universe, from the Big Bang to the ongoing processes that define its fate. The answer to the greatest, most limitless questions may lie beyond our current knowledge, and Webb's observations may ultimately be crucial in revealing new insights that could reshape how we interpret reality itself. The way forward for cosmology and space science is filled with potential. Each novel observation and piece of data from telescopes like Webb brings us closer to answering the most significant questions humankind has ever asked. How did the universe begin? What is its ultimate fate? Are there other forms of life out there? Or are we alone in this immense universe? These are questions that may one day find answers, and the James Webb Space Telescope is at the very forefront of this grand effort. The future of cosmology will likely involve a combination of new technologies, refined theories, and momentous revelations that continue to push the limits of what we know as we venture further into the unknown. One thing is certain: science, like the universe itself, is always in a state of constant expansion, driven by the quest for knowledge, discovery, and the miracle of revelation.